Let's talk about the angle between two vectors. If u and v are two non-zero vectors in an inner product space V, then the angle between u and v is the unique angle theta, where phi is less than or equal to theta is less than or equal to pi. That satisfies the following. Cosine theta is equal to the inner product of u comma v all over the length of the vector u times the length of vector v. Again, theta is the angle between u and v. Phi is the one that is outside. Next, we're going to find the angle between two vectors. Now, this looks familiar. All right, so if we want to find the angle, first thing that I need to do, and again, angle implies the cosine theta. All right, so the laws of cosines. That still holds true in this section. U dot v, I find first. Got it? Not a problem. Again, this is the same representation as this in the inner product space. So, using this as your definition, you use the dot product, and that gives you this. All right, simplified u dot v. Next, we're going to find the length of u. And again, what we're talking about is uu. There you go. And you're going to work it out and simplify, you're good to go. The length of v, again, means what in the inner product space? It means VV. But we just go straight to the square root of the first guy squared plus the second guy squared, and that gives us the square root of 29. Next is using the cosine theta formula, the laws of cosine formula. This is the inner product space formula, and we use it just like we do the dot product. Okay. Using substitution, very simple. So we can get an exact answer, we can get an approximate degree answer, and we can get an approximate rad answer. Again, how far you go with all of the decimals depends upon the book, what the author wants, or what your instructor wants. Next example, we're going to find the angle between the vectors, and they gave us f of x equals 1 and g of x equals x squared for the inner product space, which is defined by the integral from -1 to 1 of f of x times g of x dx. All right, so they already told us what our bounds were, they told us our functions, and they let us know that we're inner product space. Let's start out. All right, inner product space of f and g. And I'm just doing it a little bit more formally. F function is 1, the g of x function is x squared, and we are going to integrate. So we're just going to input our f of x and g of x, and simplifying and then integrating. Using our bounds, we get 2/3. Step 2, I want to find the length of vector f, which is the square root. Because this is the length, I'm going to put it like this because it'll help me out remember that length implies a radical. So the length of FF and F are 1. Just by definition, that's all I'm doing, folks. All right, I'm going to stop right here. I'm going to do this problem without the radicals, but I must remember to use them at the end. Why? Because this gets a little funky with notation. You're going to see it and you're going to go, what, and exactly. So what I'm going to do is remember that the radical goes on it, which is why I'm doing it like this right now. Because the length does imply that I'm going to do the square root of my answer. So let me show you why it gets a little funky. Because I don't want to take the square root of an integral. That's why I don't want to do it. So as I'm doing my integral, I'm just going to do the regular calculus. Okay, you got f of x times f of x, 1 times 1. My integrands are still the same. I'm going to work it out. The integral, wow, I'm going to integrate 1. And then from -1 to 1, I get an answer of 2. But understand, we're saying the square root of 2 because I did not want to put the square root over an integral. I don't know, that feels really weird to me. If you want to do that, you can, just so that you remember it, or just find out how you want to do it. But this is the length of vector f. We still have to do the length of g. And again, the length of g implies a square root of inner product space gg, which is the square root of x squared and x squared in the inner product, just replacing g. Again, I'm going to have to remember to put the radical in because I'm not putting the square root of an integral on it. That just feels bloody weird to me. All right, x squared times x squared is x to the 4th. I'm going to integrate. Not too bad of integration. They're really not that complicated in this section, which is nice. All right, so I end up, after I put in my integrals, or my bounds from -1 to 1, I get 2/5. But wait a second. Remember, we were talking about the length of g, which is the square root. Length is always square root. I dropped them, put the radical back in, and I get this. Either one is fine. Just depends upon what you want to do, how you want to write your answer. But in the end, you're going to have to figure out what the instructor wants. Now that we have all of that, we have to do the cosine of theta. That's what all this was about. We have the length of f, the length of g, and we do have the dot product, so to speak. So, again, all of this involves calculus. That involved the calculus, that involved. So, those are all the answers after using the integral they gave us. And we're setting it equal to cosine theta. And the hardest part for a lot of students is not the calculus, it's doing the algebra. Just understand, take it easy, go really slow. I inputted all my values for the dot product, the length of f, the length of g. And it's just, again, remembering how to do fractions and doing the algebra. Simplifying my problem, I get 5 over 3 root 5, or if you rationalize your denominator, you get the square root of 5 over 3. So cosine theta is equal to the square root of 5 over 3, and again, we want to solve for theta. So theta is equal to arc cosine of the square root of 5 over 3, exact answer. Or theta can equal either one of these answers. And again, this really should be approximate because we're using calculators. And it depends on how far your instructor wants to go or what format they want to use. That's how you actually do an inner product space using calculus. And finding the angle. Next up is orthogonal projection of u onto v. This is the formula for projection of u onto v. Please understand that I could ask you for the projection of v onto u, of which u and v would change place in that formula. There's only 2 ways to rewrite this problem, u onto v or v onto u. Again, if you do the v onto u, all of the variables will switch places, and it's not about the, given this, I will not probably give you this, I will give you this. If you do not know how to read this and how to put it into a formula, you are going to screw it up from here to here. I want to know, do you know how to read this, and do you know how to set up the formula? That's the hard part. The hard part is not using this formula, is what does this mean in reference to the formula. Please understand that. We are given vector u is 3, 7, and vector v is -1, 4. Since we are dealing with projection, new definition, orthogonal vectors. Wow, they all sound the same, don't they? Two vectors u and v in an inner product space V are said to be orthogonal if the inner product space of u and v equals 0. Not the zero vector, but 0. Definition of orthogonal: two vectors u and v belonging to R to the n are orthogonal to each other if u dot v equals 0 or the inner product of u and v equals 0. The older notation is using the perpendicular symbol for orthogonal vectors. All right, now we're on to orthogonal. Determine whether the following pairs of vectors are orthogonal. I gave you an R4 space. How do we determine if they're orthogonal? Dot product. So we're going to have the inner product space of uv is the same thing as doing u dot v. All right. The first elements, second elements, third elements, fourth elements, multiply, add like terms, and you're good to go. What did we determine from that? Since we did not get 0, this is not orthogonal. That's all it means. It's not orthogonal. What else does it mean? Well, it's not orthogonal, so therefore it's something else. That's all it means. You got to figure that out if there was more to the problem. They just want, is it orthogonal or not? It's not. It's not the shortest distance. It's not whatever it is that they're looking for. New example. They want us to figure out if these vectors are orthogonal or not. Again, inner product states basically use u dot v. That is a v, honest. Again, same thing applies as we did above. And I get an answer of 0. What does this mean? These vectors are orthogonal. Cool. Oh, goodness. Now we come to the cool part. We get to do calculus. C of -1 to 1. Now this is our bounds. That's all they're saying. They just called this guy C. Our bounds are C. So our bounds are from -1 to 1. You have an f of x function, you have a g of x function, and you're given the inner product space is this function right here. So every single thing has its own little setup in terms of inner product. As you saw, you can do R space, you can have a certain inner product space with matrices, you can have the same thing with polynomials, and you can do the same thing with functions of this sort in calculus. Show that f and g are orthogonal in the inner product space. All right, some bounds between a and b. Now, they said a and b, but they actually gave us the bounds, which were -1 to 1. But this is the generic setup of this. That is the reason why they said C is our bounds from A to B. They're referencing the formula they gave you. To prove if F is orthogonal to G, all right, we're going to use our bounds from -1 to 1, and I'm going to just put on aside the generic formula that they gave us. They're telling us this is f of x times g of x dx. This is the general setup for a calculus problem. And f of x is x, g of x is 3/2 x squared minus 1/2 when I distribute the 1/2 through. And of course dx. I'm going to distribute. This is just like a regular calculus problem, y'all. This is nothing new. It's just the setup is a little bit different in linear algebra in the way that they stated the problem. I split it up into two integrals. You can do it all in one. You integrate, and then you're going to have to deal with your bounds. When you deal with your bounds and simplify, got an answer of 0. Therefore, f and g are perpendicular or orthogonal in an inner product space. The definition that everyone loves, orthogonal projection. Let u and v be vectors in the plane. If v is non-zero, and vector u can be orthogonally projected onto vector v, So let's get this straight. I have vector v, and I have vector u. They share the same initial point. And vector v ends here somewhere. Vector v, it could have been here, could have been all the way out here, could have been way over here, doesn't matter. But for the sake of our show, it looks like vector v is out here. Wherever vector u stops, we can drop a line, a perpendicular, a shadow of that point onto vector v. It is orthogonally projected, forms a 90-degree angle, onto vector v. This is what we call an orthogonal projection. Vector p will be a new vector from the initial point that both u and v form to where the shadow drops. Because again, it's not the same as vector v, it's smaller, it's some scalar multiple of v. Therefore, vector p is a little bit different. Most of them will use vector p to make you realize that we're talking about a projection. So the formula for projection is you have u dot v up on top with the length of v squared in the denominator times vector v. That is a vector v. We call this the projection of u onto vector v. That is what this picture is showing. Again, this is a projection of u onto v. That is how you read this notation. This projection, again, p is a scalar multiple of vector v. It just means that of all the possible scalar multiples of the vector v, the orthogonal projection of u onto v is the one that is closest to u. Vector p is some scalar multiple of v because, again, p is on the same line as vector v. C of negative 1, 1, these are our bounds. We are given f of x, our vector f of x, which is x cubed minus x, and we're given a vector g of x, which is 2x minus 1. We want to find the orthogonal projection of f onto g using the inner product in C of AB. Now they gave us this. They should always give you this. This is kind of like the standard inner product for our calculus problem. Now we got to figure out the projection of f onto g. If they said f onto g, then we've got to do a couple things, okay? First off, we can still do dot product on the numerator, f times g. So we have the integral from negative 1 to 1 of f times g. Then dot product means to multiply. We're going to add or subtract like terms. All right, so we'll end up with this. Now, you guys know how to do calculus. So I'm going to skip to the very end. And once I put in my bounds, I'm going to first get negative 1 over 60. And in the second one, when I subtract my lower bounds, I get 31 over 60, and that gives me negative 8 over 15. So that is when, this is the numerator, f times g. Step 2, now understand, this is f onto g, which means g has to do a lot of work here. So we're going to find the length of g, but because we're doing calculus, I'm not going to put radicals over an integral. It just goes against my grain. So I got to remember how to do that. So I just note to self, I go, remember that. So what I'm going to do is g dot g. I'm going to multiply, add my like terms, or subtract, whatever it is that they tell me to do. And then I'm going to integrate it. My upper bounds, when I plug it in, I get 1/3 minus my lower bounds. I get negative 13 over 3, and I get 14 over 3. Now that I have my final answer, let's deal with this. We said length, and I forgot my radical, so I'm going to put my radical over it. Now, the setup, let's remember this. This is f onto g. The projection of f onto g, which means g is, we're going to be multiplying by the vector g. We're going to have the length of g squared, and we still have a dot product on top. So this is the reason why I did what I did. I didn't square my g just yet, but I just left it as the length of g. I can deal with it later. But this is f onto g. Double check, is g doing all the work in this problem? The answer is yes. Therefore, this is a great setup. Again, if this was g onto f, change everybody around. So if I'm going to do this projection, this is f times g, that was our answer. This is the length of g, now I'm going to square it, times vector g. For those of us who forgot algebra and how to do it, 14 over 3 is going to be my answer, so I'm dividing by 14 over 3. Still have this times 2x minus 1. Multiply by the reciprocal, reduce, and then you can leave it here if you want, or you can go ahead and distribute the negative 4 over 35. Either way, that's fine, whatever the book wants.